Hello everyone, I hope you all are doing great. So let's start. Today we'll be learning the KNN algorithm. KNN is a supervised machine learning algorithm which we use for our classification and sometimes regression also. So first of all, the full form of KNN is K nearest neighbor. And as the name suggests, it depends on the neighbor or the neighbor are the main factor on which our prediction will be depicted. So I will be explaining you the theoretical part, the logical part of the KNN, and then in code with an example of distance prediction. So I will be explaining you the code from line to line. And before jumping into the code, let's first understand what is KNN. So KNN is an algorithm which is used for classification. On which basis we classify? We classify on the basis of distance. And distance is the Euclidean distance we use here. Is basically an L2 norm. And the way to find out the Euclidean distance is as similar as the algebraic distance. So as the algebraic distance is x2 minus x1 whole square, y2 minus y1 whole square, and if it is 3D, z2 minus z1 whole square, that's all root. That is our algebraic sum or distance, and that is same. Euclidean distance is that only. And let's see an example. See, this is an example where we have three different data. Let's say 1, 2, 3, 4, 5, 6, 7. The 8 data we have, and then this is our subject data or the test data. We have to classify it into any of these three classes. So our first step is to find out the Euclidean distance from each and every point in the data. So we find out the distance of this test subject from each and every point given in the data. Then we arrange those distances in an ascending order, or we can say an increasing order. And then comes the part of the value of k, which is very important. I will tell you later how it is to get the optimum value of k. So k is basically the number of neighbors on which basis of which we will be predicting our output. So see, if the k value is 3, so in this example I am having the k equals to 3. So this means I will be predicting my output on basis of these top 3 values. See these 3 values. In these 3 values, the two subjects or the two distances are from yellow and one is from green. So here I can see that the majority is yellow. So I will classify my test subject into yellow class. And suppose I was having the value of k equals to 5. And so suppose the list was like this: 1, 2, 3, 4, 5. These 5 elements were in the top, or you can say the least distance to the subject. Then the majority will be green, then the subject will be classified into green category, or we can say the green class. So see, if the value of k changes, then the prediction or the class which we are assigning to the subject is also changing. So it is very important to get the optimum value, or we can say the uh, least least mistake value, or can we say the most accurate value for k. For that we use in another kind of code, calculator. So now let's start with the code. See, first of all, we imported all the necessary libraries which we'll be using in the code. First of all, pandas for the data frames, then skittlers, different codes. So for this line, we loaded the test cancer. So we just grab the data available in the skittler library for the breast cancer experiment. This is the example. Then we imported the train test split function, then the student scalar function. I'll telling you all these functions. Then the k-neighbor classifier, which is our main function for KNN algorithm. Then this accuracy score and classification reports for printing our outputs. So now let's start. First of all, we grab the data from the library. Then we load it into the data variable where I can use this. And then now I split it into x and y. So x and y are, see, the x is the features like the age of the patient, the glucose level of the patient, the BP problems of the patient, and different like this. And y is the data we can see on the basis of x whether the patient was having cancer or not. That is y. So there is 0, the logical 0 means malignant and 1 means benign. So this means patient was having cancer, and this means benign, or 1 means patient was not having cancer. Now we will split our data into two parts, the test part and the train part. See, if I am having our data, I will just split into two parts. See, this x1 test size 0.2. This means I will be distributing my data 80% in the train part and the 20% into test part. See, I can change this value from 0.2 to 0.314 anything. But if we increase this value, which will mean that we will decreasing the train data, so our accuracy will be less. If I train my algorithm less, I will be giving him less data, then the accuracy will also be hindered, the accuracy will also come less. That's why we prefer to just use kind of standardized or general 0.2 or 0.3 for test size. And this stratifying why this we use for, you can say, the maintaining the ratios of patients having cancer and not having cancer in both sides. Suppose if I am splitting the data, my test data might have more number of patients having cancer as compared to non-cancer patients. Trained data might have less. So to maintain the ratio of the patients having cancer and not having cancer in both the parts, test and the trained part, we use this 35y function. Okay. Now scalar equals to standard scalar. So this standard scalar function we use to standardize the scalar to make things more comparable. Suppose I can compare, let's see, the age of a patient and the BP levels of the glucose of the patient. I can't compare those because these are kind of different variables. I can't compare some speed with weight. Okay, now so for that comparison, we just standardize those scalars from 0 to 1 to make it comparable, and so we can use it very easily. That's why we use the standard scalar to standardize them from 0 to 1. Then extend and extend the data, the x we standardize using this function. Now build KNN model. So here comes the main part, KNN models, where we'll be applying the logic of the KNN algorithm. Here we give k equals to 5. The n neighbor means the number of neighbors we will be using for prediction, or the value of k is 5. Now I put my x and y trained data, the training data, into this algorithm to get me the outputs. See, let me show you something. See, this is the kind of main function which is present inside the k-neighbor classifier. So see, this function is mainly used for, or let's say, use of this function is to get the optimum value k. As earlier I told you, if we vary the value of k, our task may change, or we can say our accuracy may vary. So to get the optimum value, or we can say the best accuracy from our code, we use this. Here's the code. See here I use the for loop for k from 1 to 21, and generally, not generally, main. This is kind of compulsion, you can say, but no compulsion. We use the value of k equals to 4, so it is easier to classify. Suppose 3, then 2 measure, then it will classify into that 5 for 3, that half. But if suppose we are having k equals to 4, then half of it will be, let's say, not easier to classify the patient. See, now here I will be training the fitting the data into our k-neighbor classifier and then predicting the accuracy. And if the accuracy is less, I will get another value best accuracy, which will contain our best accuracy. And if the accuracy of this value of any value of k is greater than expected accuracy, then I will store that value of accuracy into best accuracy. After the application of this code, I will get the best value of k, or you can say the optimum value of k, for which our code will give us best accuracy. So this is the accuracy part. And now just after assigning the values into the function for the k neighbor, now I will be predicting the output. So here we will be predicting the y predict equals to kn dot predict k test values. So here we will be predicting the output of the test data we used to find whether the patient was having cancer or not, and the results we will be printing the data inside, accuracy of the data, then the precision and the equal values. So see, here I got accuracy equals to 0.95. See, 0.95 doesn't mean out of 100 I got 0.95. As we standardize the scalar from 0 to 1, every scalar, so this is also like standardized like that. So this means I was having 95% accuracy. As 0 from 1 to 0.95 will equals to 95%. So the accuracy of my code is 95%. And this is our classification report. In classification report, we have precision, recall, F1 scores. So precision is basically the number of positives in our predicted data. See, if our test data was having 10 patients which were having cancer, and my prediction from this code was like 9. So this is showing that percentage, that how accurately I predicted from the test data. And this recall value is the positives which were overall in the data, means the test data and the train data inclusively. How many, what was the ratio of those, or we can say the percentage. And F1 score is basically the, let's say, comparison ratio, I can say. It's basically the comparison we can say, or we can say the normalizing these precision and recall. Then we get the F1 score. See, 9.5, 9.3, the average is 0.9. Like this here also 0.97. And these are our micro averages and weighted averages for the output. So I hope you understand the whole algorithm very efficiently as I had tried my best. So thank you.